Hello, everyone. So, for today, I actually wanted to discuss one thing which in my last tutorial, actually left it unexplained. For example, um, we were working with Postgres and we ran some queries on indexed and non-indexed columns. And we also ran a command which was named vacuum and it was ran on analyze. At that time, honestly, I did not myself have an idea how exactly vacuum works and what was the actual reason for having vacuum, what it was doing. Okay. So for today's video, I actually decided why not explain how actually what it actually does, the reason behind it. But before even that, I think one question which I had in my mind for a long time that we need to understand how even a data is stored inside the database, okay, or the disk, the physical location. I've actually attached an external monitor, so that is why I might be looking above the place. So don't worry about that. So as you can see here, we have a page one and a page two. Just ignore page two for now. Let's just focus on page one, what it is. So it's a position or a physical location inside the disk. Okay, that is how our rows are stored. Okay, but not only that, a row actually has a specific identifier to it so that we can identify it, later reference it using indexes if we have index, of course. And it is called as tuple ID because it's a tuple. Why it's a tuple? If you have used Python, you might know that tuples are actually a pair of values. It has the page number, which particular page we are at, and the offset. Of course, we are talking about memory. So in memory, things are, placed in order of offsets. 8, 4, offset of maybe 1024, whatever. So that is how the rows are actually stored. One another interesting thing when we have an index, okay, which is also stored on the disk location, a particular index actually points to this tuple ID, and that is how we actually specifically know when we fetch an index and we go to a particular index value, this is the reason we know that where we have to jump inside the disk, which particular page we have to fetch. Okay, that is how we know because the TID, tuple ID, is the reference here. Now, what happens is we have a very special scenario. We run a large query, update query, for example. I've actually given an example here as well, but probably, yeah. So we have a table of orders. Let's just suppose we have an e-commerce store. Okay, we run a query, an update query, and it actually sets the status to ship. Now remember that this particular column is not indexed. We're just going to actually first understand how the normal form of this works, the problem, and then an optimization. So we run an update query, and this happens. It actually updates million rows, maybe thousands of rows, but for some reason it fails. And now our database, whatever engine we are using MySQL or Postgres or maybe Oracle. So what happens is now we have different choices. What are we going to do with the rows? Because we have ran a transaction, etc. Everything happens in transaction and database, unless we do not decide to. But we ran a transaction and it updated thousands of millions of rows. And now what happened is that it actually rolled back. Mm, And when we update certain rows, what we do is it does not happen instantly and it comes with its problems. We updated a row. So what we do is we create a new tuple ID. We actually store that row at a new physical location inside the disk and give it a new tuple ID. Okay, that is something which happens. Now the problem is once the transaction fails, how are we going to clean this mess? Either we are going to wait for it or like asynchronously clean it after, like take some time. or asynchronously clear this or clean this as a sub process, or you can say kind of a cron job. Or we can, like MySQL, we can clean it, and until it is not clean, we will not allow any other transaction to take place. Okay, each comes with its own trade-offs. Postgres is actually the first one. It actually cleans those things periodically using vacuum command. So the vacuum command is one which actually clean those rows, because we have created new rows and the previous rows are actually pointing to the new rows. So it's actually pointing to rows which were rolled back, and it's actually quite a mess. So we have to clean them because, for example, I updated 100 rows. My transaction updated 100 rows, and I rolled back the transaction. Now, if I have rolled back the transaction, and if I have updated, I come back, okay, and I run another transaction. I go to the database. I fetch those 100 rows plus 50 more rows. The 50 rows are fine, but the 100 rows, I'm not going to fetch them. It's true that databases are matured enough that they won't actually fetch those new rows. Okay, they're not going to fetch, for example, let's just suppose these. In case of row 1, 2, 3, for example, if they are, let's just try to copy them here. Why does it happen with me? Ah, actually, here's a copy command which we use. Yeah, yeah. See, I forget the command usually. So this is the new row locations in the memory. What happens is each database engine would actually check the transaction and will make sure that it wasn't rolled back. But this has a cost. I'm actually going over 100 rows and checking their transaction status. And if it was rolled back, I'm not going to fetch them, but it is taking a lot of the cost. Okay, so that is why we run the vacuum command, which makes sure that these are removed. But even beside that, the interesting part, or which actually instead of doing all this stuff, like because it is happening inside page to a new physical memory location, there is actually another way. And yeah, one another important stuff. For example, if you have updated a particular row, each and every index value in that particular table, for example, it's orders table and it has three row indexes: primary key on ID, customer ID, and status. All of those indexes will be updated to point to the new tuple ID. Okay, so if we ran how we updated 1 million rows, and those 1 million rows are actually being pointed by maybe, for example, four indexes. So you can see we have to now update almost 4 million indexes. So you can imagine the amount of work which has to be done if things are not taken care of. That is why optimizations are very interesting part here. Heap-only tuple. And actually, this was called hot. Not the one we usually hear to, but I, first time I heard it, I was like, what does it mean? So it's heap-only tuples. Okay. What happens is, and this is something which Postgres does. I'm not sure how MySQL and other database engines do it, but I might read about it and share with you later on. But what happens is that when we create a new row and provide it a new tuple ID, we place that new row, and all of this is happening in the physical location, the disk. Okay, do not consider that it's happening in the random access memory RAM. What we do is we point the old tuple, the row tuple, I might mispronounce it, interchangeably. So it actually will point to the new row, okay? And we will place that new row tuple ID in the same page as the original or the old row. So it saves our time because now we do not have to actually, create another page and save those rows in new locations. So it is much better optimization than doing the stuff which we did previously. Okay. We do not have to go to another physical memory location, and it also saves us the time of the new tuple ID. because we are not going to have a new page. We might have a different offset maybe, and even we do not actually have a different offset because the old row will be pointing to the new row. So, for example, when Postgres comes or reads that particular old row, it will actually find a pointer and it will say, oh yeah, this is actually the old row. Now I have to point, and it will follow that pointer and will move to the new row and read the data from there. So this is actually what is called as heap-only tuple, and the and this is an optimization, of course, as compared to what we saw earlier. Remember that it works for the cases where none of the updated columns are part of any index. Okay, if we have particular updated particular columns in a row and those columns are not indexed, okay, then it is going to work. And the new tuple version fits on the same page. Yeah, there is an also interesting thing. That, for example, I'm just actually trying to explain it. Please pardon the numbering if I write it wrong because it's not important. 5 and 4. Here we can see we have only one space left, so it worked. And if, for example, if we try to update the row 2 and it actually has row 2n, now we cannot fit it inside this page because it's already filled up. And we will eventually have to create another page. And there is an interesting term about it, which is called as fill factor. So setting fill factor to 90% means that the 10% of the space of the page will be actually reserved for this kind of particular scenario where we will have to point all rows to Neuro. I've also many questions around this concept. Still, I'm actually exploring. So if I find something new, I will definitely share with you guys. But of course, if you have any insights about this, if you have already used it, let me know because I'm definitely interested to hear more about this. I will explore it on my own. There's one more. Yeah, if the page is packed 100% full, there's no room to squeeze the new table onto the same page. Okay, so heap only tuples fails. New tuple goes to elsewhere. Of course, a new disk page. Indexes must be updated the normal, expensive way. Now, since we could not do it in the same page, we will resort back to our old approach of creating a new page pointing to the new tuple IDs. Since we have changed tuple IDs, of course, we will have to do this stuff here, and it's going to cost us a lot of time. So yeah, that was it. And I hope you learned something new, just like me. And have a good day. Goodbye.